So with a little delay, I think we are now ready to start. Just let me know, can you hear me? Can someone reply?
Yes, sir.
Okay, thank you. So the topic which I want to discuss today is vector spaces. Another name, so let me first turn on the mic. So vector spaces, another name for the same category is, people also call them linear spaces. And so what are they? Well, we have encountered objects which we called the column vectors. They were objects like this. So why I call them a vector? Well, in this case, the connection is very simple. There's a connection to geometrical vectors. And what's the connection? If I consider this kind of a three-dimensional space, with x, y, and z axis. And for example, if I take this vector, this column vector, 2, 3, 1, so it will be a vector in this space starting from origin and the tip at this point with coordinates 2, 3, 1. So it's something like some guy going like this. So the coordinates of this point are 2, 3, 1, going 2 steps in the x direction, 3 steps in the y, and 1 step towards the z axis. And if I have, so this is for 3 dimensions. If I consider an object like this, 2, then this guy is just the same thing, but with 2 dimensions now. So a vector in a plane. Similarly, I can consider this object is pointing in this direction with the tip at 3, -1. So it can describe this object describes a vector in 2D. But for vectors, we have operations like we can add vectors. This is for geometrical vectors. And the rule is the head to tail rule. If I work out the head to tail rule, what turns out is that their representation over here is just that if I add these two vectors, the head to tail rule gives me the resultant vector where I just add the components. So just like you have a rule for addition of geometrical vectors, that translates into a rule for adding, I don't know what's going on. These column vectors. Then there's another operation on these geometrical vectors, which is that you can change the length. Or you can say that you can scale the vectors. Okay, मेरे पास, if I have this guy, it's this vector, I can double its length or triple it if I want. And the resultant vector, so I do it by multiplying with some numbers. The resultant vectors just have components defined through this. So this property that you can scale the vectors and get new ones is true for column vectors as well. So whenever you see a column vector, you can think of it, you can translate it into a geometrical vector, something living in the, so a column vector with 2 or 3 components can be translated into, can be thought of as describing geometrical vectors in 2D or 3D respectively. Now, what about if you have an n-dimensional column? So we had objects like these. Where these ai are from the real number. So you just imagine that instead of 3 axes, like when you have 2 numbers, then you think that you have 2 axes. When you have 3 components in this column, you have 3 axes. So you just imagine that you have some kind of a space with n axes. You cannot really imagine it in your mind. You just can deal with it by using the same rules which you were using for 2 and 3 dimensions. So you just have an extra axis which is perpendicular to your previous axis. Since the space we live in is 3-dimensional, so we cannot really imagine in our mind more dimensions, but we can deal with them very easily. We are just using the same rules which we were using for 2 and 3 dimensions, and we just imagine that you have a higher dimensional space now. So this space would be called the Rn, where you have n axis. And a column translates to a point with coordinates, or I should say a vector with tip at a point with coordinates which are given like this, which are these coordinates. Everything is going wrong today. Now, we have these operations which we have, yeah. Is there a question? There is another operation or a property for geometrical vectors. That if I have a vector like this, I have a vector in the opposite direction as well. And when I add these, you get 0. So if I start from this point, this is my vector, and I consider the vector in the opposite direction and add them, the head to tail rule tells me that I come back to the 0, the origin of the axis. So that vector, the sum where you are not moving anywhere, you are getting this vector back. This vector is called the 0 vector. So you have 0 vector in your space, which is that you do not even move away from the origin. And you have this property that if I scale any vector, so if you are given this vector and I scale it by multiplying with 0, so I bring it down to collapse to the origin. So scaling with 0 number gives me the 0 vector, which is this vector. Because that's the rule. You multiply your number with the components. So when you will multiply with a 0, you will come back to the origin. These properties, which are pretty obvious, you all know about these. I'm just collecting them again over here. Then this idea that for every vector you have the vector in the opposite direction, and when you add those two, you get a 0. This means that for any vector v, you have a vector minus v, which is in opposite direction, so to say. And its property is that when you add these two guys, so minus v is just a symbol for this, you get the 0 vector. You come back to origin. And the property of this, how this guy is defined, this is defined as that vector that if I add it to any other vector, that vector does not change. That's the 0 vector. So these properties which are obvious for the geometric vectors and which you can translate to column vectors as well, because column vectors are just describing for you the geometrical vectors. They are a representation of the geometry. You can translate back and forth. They are true for both. So what you do is you want to distill these properties, these facts about vectors into a more abstract form. So what you're going to say is that any objects which have these properties, I can think of them as vectors. And that will give you the vector space. So a vector space V is a set it's such a set that its elements are supposed to be vectors. You just call them vectors, which have all these properties. So the properties you have to list is that if I take two guys from set, now this could be a geometric vector, a column vector, or any other object. If I take two, then I should be able to add them and scale them. So I can combinedly write it like this. That I can scale these guys. Scaling means I can multiply with numbers. There should be a multiplication with numbers should be defined over there. And then I can add them. So maybe I should write over here that this operation is defined. This is multiplication with numbers. In case of column vectors, that was just multiplying each component. In case of the geometric vectors, this translated into scaling by this size. And this multiplication by numbers is defined and addition is defined. That you take two vectors, you can add them. So these two things, these operations exist, and that I have combinedly written over here. Where these A and B, they are just numbers. They belong to real. And one thing you want from your addition, it doesn't matter which order you add. It's kind of obvious. Most of the objects we will consider, they will have this property would be almost by definition, the way we will define those objects. Then you have this property that a vector 0 also exists, is in your set with property that 0 plus any vector is that vector back. So just like you have 0 in your geometric space, you have a 0, you want to retain that property over here. And lastly, you want this. that if I multiply any vector by 1, I get the vector back. And then you also have, I think probably I can combinedly write those things, that you have these distributive laws. This is just this, and these kind of obvious things hold. So you can stop here, and these are the main properties you have. Well, I had also the inverse of a vector, like in the opposite direction. Those things will also be there, but it turns out that that property you can derive from these. So you don't have to write it in definition, or if you want, you can write, but you can get it from here. So if you want to retain the minimum number of properties in the definition, the other one, some of them you can derive. But all the obvious things for vector spaces, for geometrical vectors, turn out to be true, and you want to retain all of those. So for example, you can show that if I consider, because I can multiply with any number, so I can consider this multiplication. And then whatever vector I get over here has the property that when I add it to V, I use my distributive law over here. And this gives me 0 times V. And 0 times V, I will prove for you that it's 0. If I could prove this, if this is true, which was true for geometric vectors, that if you multiply any vector by 0, you scale it to 0, you get the 0 vector, then this guy would just be minus V. This would mean that for any vector, there exists another vector minus V such that when you add these, you get the 0 vector. So you can kind of reverse in these abstract objects, you can reverse direction. Now, how do I show this? Well, I can write this V is just because I assume that any V is 1 times V. This I threw it in my properties. But 1 is 1 plus 0. Right? So now I use again the distributive law. So that means this guy is the 0 vector because I'm adding it to V and I get V back. So this implies 0V is the 0 vector. So the point is, you don't have to the main point over here is that if you consider any objects which obey the properties of vectors which you are familiar with in vector spaces and in geometric vectors, you want to call them vectors because using these properties, the intuition you have for geometric vectors will be brought into those objects, and you can deal them using your geometric intuition. And any result, why we define categories, because if I use these rules to get any result, will be true for all objects who are in that category. So if I prove something using only these properties, then that result will be true for any object which is a vector space. Now the main test, so you want to check how to check if a set is a vector space. The distributive laws, they will be just understood to be there the way you define it. The main test is you check you pick any arbitrary elements from your set and you multiply with arbitrary numbers and you make this combination. If it's still in your set, if you can find this combination in your set, that means all the previous properties will hold. If this fails, you are just doomed. It's not a vector space. Because I can choose over here this number. So this will give me 0. So I will then know that 0 exists. I can choose A to be 1 and B to be, for example, A to be -1 and B to be 0. This will give me minus V1 for an arbitrary V1. So inverse vector, the reverse vector will also exist. So the main thing to test is this. Main property of vectors is that you can add them. You can add them and you can scale them. So you can multiply with numbers and then you can add these objects. So if you are able to do that, other things usually follow. So let's take an example. All column vectors of size n. So I can check that if I take any two and multiply, so these are two arbitrary. A1, A2, AN could be anything. This is equal to by the rules which we have set out for the column vectors. Sorry, this is C1, this is C2, this is C1, this is C1, and this is C2. But these are just some numbers. And since my space was all column vectors, so this does belong to, so if I call this space Rn, so this does belong to Rn. So this would be a vector space. Let's take another example. So your space is column vectors of this form. So I'm not taking all the column vectors which have two components. I'm picking these specific kinds of column vectors. So is this a space, vector space? Well, all you have to do is pick two objects. So let me pick two arbitrary objects. And by the rules of this addition, so this thing C1A1 plus C2A2 is just another number. So I can call it D1. So it is of that form because A was any arbitrary number. So D1 is an arbitrary is a number. So this is back in my space V. So that means these objects, if I collect all such vectors, they form a vector space. And let's take another example. This time my space is this going to be a vector space? Let's check. A11. Now C1 and C2 could be anything, but my space was defined that the second component has to be 1. So this does not belong to V. Or you can simply check that if I add this vector to itself, I get a 2 down here. Don't want it. Or it does not belong to my original space. So this is not a vector space. But if I consider this guy, this time you can check. You do get it back. You do get a member. So you can add the vectors, these objects in this set. So this is a vector space. So you can see actually that in this example, I could replace 1 by any number and it would still not be a vector space, except when I put a 0. 0 is special somehow in these two examples. So let's now consider slightly more non-trivial examples. You have a m by n matrix. Now, what would be the zero vector over here? The zero matrix this has the property that for any A in this, so this acts like a zero object. And I do have, for any A, I can define minus A, just multiplying minus to every element of this A. And I know that when I add these two matrices, I get the zero matrix. So again, if I check, since addition is defined, this is still gives me some matrix D, which is still in M, matrix M cross N in this class. So all matrices of any size, they form a vector space. So this is a vector space. Let's consider this example. So you have polynomials. So you have some variable x, one single variable x, and this n means that you are considering expressions in this x up to power n. Where these AIs are just some arbitrary numbers. You collect all of these with any arbitrary numbers, and then obviously you can very easily see that if I add 2, so if P of x and Q of x are two polynomials of degree n, I multiply these two guys. So आपके जो algebra के rules हैं, you know that you have to collect the coefficients of equal powers. So you get something like this. C1 इसका जो coefficient है, Cn an, C1 an plus C2 an dash, where an dash is the coefficient of the second polynomial. You will have things like that. And in the end, you just get another expression of a polynomial. So this is also a vector space. What would be the zero polynomial over here? Zero vector would be just this polynomial where you put all the coefficients equal to 0, and that just is a zero number, because you add that polynomial to any polynomial, it doesn't change. And you can have the negative of a polynomial, just reverse the coefficients, and when you will add, then you will get the 0. So the reverse vectors, well, technically people call it additive inverse, but I'm just using colloquial language. Reverse vectors are just minus times the polynomial. It exists, and you have a vector space. Let's take another example. So suppose you have functions from R to R, functions like these. I can define an addition on them. If I take two functions, what do they do to any point? You find the value of the first function and add to it the value of the second function. This is the definition of addition. And how do you multiply a function with a number? Well, you just evaluate f of x and multiply with the number. So a of f is a new function, f1 plus f2 is a new function, let's call it g of x. So multiplication and addition is defined, so this has a chance of being a vector space. And under this rule, you can actually do that, it's still a function. And choose a is equal to 0, you get the 0 function. 0 function is, it takes any point and maps it to 0. You can check that if I use the rule of addition of functions, the 0 function does not change the original function because the second term will be 0 and I'll just get f1 back. And similarly, you have the minus function. So it's a vector space. I'm just going to go over the time by 15 minutes because we lost 15 minutes in the beginning. If you need to leave, you can leave. So any question from these examples or in the definition? So we have now, so after these definitions and examples, let's go to some other concepts related to vector spaces. So what's a subspace? So if you have a vector space, a subset of V is a subspace if it itself is a vector space. So what could be an example? If I consider this three-dimensional space, R3, this forms a vector space because at each point I can consider the vector. Now suppose in this vector space, I say that I'm going to only consider vectors which lie in xy plane. Then if I add those two vectors which are in xy plane, I'll get another vector in xy plane. So xy plane, vectors in xy plane, they are a space onto themselves. So xy plane would be a subspace of three-dimensional vector space. And from our previous examples, so we had this space. This space. This is a subset where A were arbitrary. This is a subset of R2, obviously because it's a it's a column vector with two components. So it's every element of V is an element of R2, but it doesn't cover all of the R2. So it's a subset. And we saw that it's a space. It's a vector space. So this is V is a subspace of R2. Similarly, this V is a subspace. But we saw that this subset this set is a subset of R2, but not a vector space, not a subspace, because it's not a vector space. By the way, what about these guys? This subspace, geometrically, what is it representing? So I have two column vectors of two dimension. They geometrically, I can think of them as a two-dimensional plane, vectors in 2D. So when I make the second thing 0, that means y is remaining 0. So this is giving me this line, which is also a space. A line or vectors in one direction is a space itself. And if I consider this one, A to A, that means whatever component I have for in x direction, I have twice the component in y direction. So this would be a member of it. Then I multiply with any number. I keep changing its size. So it will give me this line. So any line in 2D would be a subspace. Similarly, any plane in 3D, because I can add vectors in that plane and I'll get the vectors back in that plane, any plane in 3D would be a subspace. So like we had this example. This is a subspace, xy. But I can consider any other plane. I consider two vectors. Let's say, for example, here. This would be a subspace. And any plane tilted along any angle, well, would give me another subspace. I can, for example, take another example. I consider this space and then consider a subset of it of anti-symmetric matrices. That means this set, let's call it A, are matrices of this form. These Aij belong to R. Well, let's not call them they are not really anti-symmetric. It just has this property that on the diagonal you have some numbers, and off diagonal a12 is equal to minus a12. This number is minus of that. So is it a subspace? It is, because if I do this, where A and B are from this set, I still get over here, and over here I get यहाँ पे arbitrary numbers हैं. So this, I do get it back. I do get an element of the same set. So these guys, this is a vector space. That means it's a subspace of these matrices. Let's take another example. So let those functions so all the functions which satisfy this equation, whose double derivative plus the function itself is 0. So when you put such a condition, this is called a differential equation, where you are relating the derivatives of a function among themselves or with the function and putting some condition. So all the functions which have this property will be called, so f belonging to f are called solutions of this differential equation, because they satisfy this equation, so they are the solutions. So I'm saying, in other words, are the solutions of this differential equations a subspace of the full space of functions? Well, you can check. If f1 and f2 are two solutions, then alpha f1 plus beta f2, if I check that if this guy satisfies, because derivative is linear, I can collect these terms. Now f1 and f2 belong to that set. They are the solutions. So this gives me 0 back. So I have checked the main property, and 0 function also obviously satisfies the equation. That belongs to that set. And since I have checked this, so minus f also is there. So solutions of a differential equation, of a, I should say, linear differential equation, we don't have to go into the types of differential equation. Let's just consider this differential equation which I have given you, its solution, they form a vector space. So the solutions are a subspace of the full space of solutions. which example, and full space of solution is a vector space. We just saw it before. Let's take another example. So let's consider a fixed m by n matrix. It's a fixed matrix. And then I consider this set which is all solutions of this equation. So A is a matrix m by n, so it can act on an n column vector, right? So these guys are n column vectors. And I'm collecting all the vectors, n column vectors, which satisfy this equation. So I can write it also like this. I have a subset of n column vectors such that this is true. I get the zero vector on the other side. So we have seen these kind of equations before. And now you can again very easily check that if I have two solutions, then just by distributive law of matrix multiplication, this will be zero. So this space of all solutions, if you are given a matrix, construct the homogeneous equation. Remember this equation we had called the homogeneous equation, where the right hand side of coefficients, constants is zero. So this is called the n of A is called the null space. So it is saying that null space of A is a subspace of Rn, n column vectors for A m by n. Let's take a further example of this null space. So suppose you are given this matrix. If I write the homogeneous equation, I want to find all the solutions. So find the null space for this. So first of all, it acts on two component column vectors. So you're looking for objects of this kind. And to solve this equation, you have to write this augmented matrix. Now, the left This guy, the left-hand side, is already in reduced echelon form. Because it is, and x3 and x4 are free. That means I can write the solution like this. X3 is some arbitrary, completely arbitrary. X4 is completely arbitrary, so I just call them alpha and beta. And from this equation, x1 is alpha minus beta, and x2 is minus 2 alpha plus beta, where alpha beta belong to R and arbitrary. Oh, sorry, I was not looking for these kinds of guys. M rows and N columns. So I was looking for an N component vector. So the subspace consists of vectors of this kind. The null space. Alpha beta completely arbitrary and is a subset of R4. So any of this, I can also break this up and write like this. Now just this expression gives me an idea that I have a space, but I'm generating all that space by, in a sense, by two vectors. Generated, well, the correct word is spanned. People call it spanned. Two fixed vectors. It's a full space, but all you need is these two vectors and then all linear combinations of them. Multiply them with arbitrary numbers. Alpha, beta are completely arbitrary, and consider all the linear combinations. The space which you make up is your null space. So this idea, exists for vector spaces in general. Span of a set of vectors. So if you are given any set of vectors, the span, let's say this is some W set, is all vectors of the form with alpha I arbitrary. Consider all linear combinations. Multiply these vectors with all possible numbers and add. That set would be the span of your W. Now, if I give you, let's come back to our three-dimensional, or let's say two-dimensional geometry. I told you I'll go up by 10 minutes, 15 minutes. If you want to leave, you can go. Because we started 15 minutes late. So if I consider, you have heard of these unit vectors I and j. If I consider these and make all linear combinations, that would be the span. But you know already that if you have any vector in 2 dimension, you can write it like this. This is like I, and this is like j. So the span of these two vectors, 0, 1 and 1, 0, or I and j, is the full 2-dimensional R2. Because any column vector with two components which fills the whole plane can be written as a linear combination. So the span is complete R2. What would be the span of so now I'm considering three-dimensional space, vectors with three components. One is in I direction and one is pointing, let's say, let me put one here, is sticking out like this. So it will fill out that plane. Now, this is an extremely important result, which is kind of obvious. Okay, I told you you can leave. So in this example, we saw that if I take two vectors, I took two very special vectors, 1, 0 and 0, 1, and the span turned out to be a vector space. It was the full R2. In case of null space, which was a vector space, it was span of two vectors again. So does the span, if I pick out any arbitrary number of vectors from a vector space, is the span always a vector space? That's the question. And this theorem says that this is true. Span of any number of arbitrary vector is a subspace of V. So what you need to do? All you need to do is pick any two objects from the span and show that it's any arbitrary objects. How do you tell that if the span is a vector space? You pick any two arbitrary objects and check if the linear combination is back in the span. So if they are in the span, that means I can write this like this, and W would again be of this form with some other constants. Because in the span, only those vectors are there which can be written as a linear combination. Now I just check. So this is just which is again in span, because all I'm doing is this is also in span because it's again a linear combination of those same vectors. So span is a subspace. Span of any number of vectors is always a subspace. Then you can talk about the spanning set of a vector space V. So if you have a set, let's say you collect these guys, m of them, and it turns out, you know that the span, if I span these vectors, I will get a vector space, which will be a subspace of V. But if it turns out that the span is the space V itself, the subspace is the vector space itself, so you are generating the whole space, then this set would be called the spanning set. So you can, for example, immediately tell me what is the spanning, can you give me a spanning set for two-dimensional plane? What would be the vectors which can span the whole two-dimensional plane? It's just I and j, the unit vector I and j, because any vector, if I span these, I get all the vectors. So spanning set, one spanning set because linear combination, the span of it is of this type, and these guys, these for all arbitrary a, b, so this set is equal to R2. If I want to consider span or spanning set, a spanning set for M2 cross 2, I can write these. This is a spanning set for two-dimensional matrices. Why? Because any matrix, this is any arbitrary matrix, A, B, C, D, can be written as a linear combination of these sets. So let's stop here.